Good afternoon all. Welcome to the 7th week tutorial session of NPTEL course Thermal Engineering Basic and Applied. My name is Ananthakrishnan. I'm a PhD scholar from Department of Mechanical Engineering, IIT Delhi. I do this problem solving session as part of my PMRF TA duty. So in this week, we'll see a few numericals and multiple choice questions based on steam analysis in flow analysis of steam in nozzle, mass flow rate, critical pressure ratio, and its physical significance, nozzle efficiency, and the factors that affect the efficiency. And we won't touch upon steam turbines in this session. We'll look about the steam turbine in the next session. We'll see a numerical based on the steam turbine, not the theory. Okay, look into the first problem. It's a multiple choice question. I'll try to solve it. The question is, due to the frictional effect, the dryness fraction of the steam at the exit of the nozzle increases, decreases, or remains the same. So the answer is increases. Once frictional effects are introduced in the steam nozzle, there will be a reduction in enthalpy drop. Then there will be an increase in specific volume. And there will be a reheating of the steam due to the frictional effect, resulting in improved dryness fraction. So the frictional effect increases the dryness fraction of the steam at the exit of the nozzle. That's a straightforward one. In the second problem, for an isentropic compressible flow through a converging section, in order to increase the velocity in the direction of the flow, the Mach number must be equal to 1, greater than 1, less than 1, none of the above. So answer is less than 1. So it's a converging duct. So Mach number should be less than 1, so that as we go further inside, the velocity increases. But if the Mach number will be greater than 1, the converging section will be acting as a diffuser, whereby the velocity decreases. So that is case of a supersonic flow. Looking at the third problem. At the critical pressure ratio, the mass flow rate at the exit of the nozzle is minimum, maximum, zero, none of the above. Think about it. So the question is, at the critical pressure ratio, the mass flow rate at the exit of the nozzle is minimum, maximum, or zero. So if we try to plot the mass flow rate against the pressure ratio, so it will have this kind of a trend. So this pressure ratio, P star divided by P, P by P star. This is the axis. So the pressure at any point of the nozzle divided by the outlet pressure, that is the pressure ratio. Critical pressure ratio is the point. Critical pressure ratio is the ratio so when the mass flow rate at the outlet is the maximum, then the basically the outlet pressure, the this ratio is defined only when the mass flow rate of the exit of the nozzle, mass flow rate of the exit of the nozzle is maximum. So in the case of an nozzle, so this is the entry point and this is the exit point. So the mass flow rate or the discharge equation could be represented as root of 2 divided by n minus 1 p1 divided by p into p1 divided by p2 the whole power to p2 divided by p1 the whole power n plus 1 divided by n. So for maximum discharge at the exit, we will differentiate this equation and put it equal to 0. And then we'll get a ratio of the pressures P2 divided by P1. That is the output pressure divided by input pressure, the outlet pressure divided by inlet pressure equal to 2 divided by n plus 1 divided by n divided by n minus 1. So for it's a reverse analysis. For the mass flow rate to be maximum at the exit of the nozzle, the pressure at the exit should be equal to the critical pressure. So this P2 is the pressure at the throat of the nozzle and P1 is the pressure at the entry point. So basically P2 is the, in this particular point, I will get the critical pressure ratio, P2 by P1. So the question says at the critical pressure ratio, the mass flow rate at the exit of the nozzle will be maximum. So it's a reverse analysis which I have shown here. Look into the fourth problem, it's a numerical. I'll try to solve it. Okay, it's a numerical problem. Steam is expanded in a set of nozzles from 10 bar to 10 bar 300 degrees Celsius to 2 bar. Are the nozzles convergent or convergent divergent? Neglecting the initial velocity, find the minimum area of the nozzles to flow 1 kg of steam. Assume isentropic expansion. So it's expanded from 10 bar 300 degrees Celsius to 2 bar. So we need to find whether the nozzles are convergent or convergent divergent. We need to neglect the initial velocity, and to calculate this one, we need to find the area of the nozzle. So could be assumed that can be a convergent divergent nozzle. So in this case, the starting point will be 0 and the ending point will be 1, and this is the throat section. So if the exit velocity, if this exit velocity is higher than the so if this is a convergent divergent section, so if it is acting as a nozzle, then the exit velocity will be higher than that of the incoming velocity. So that's a straightforward thing. What we try to do is that we try to tackle this problem in a straightforward manner. So we know the critical pressure ratio for maximum flow rate. P star divided by P0 is equal to 2 by gamma plus 1 divided by gamma minus 1. Steam at the inlet is in a superheated condition. Ten bar 300 degrees Celsius. We can take gamma equal to 1.3 for superheated steam, and gamma equal to 1.135 for dry saturated steam. So we know the value of P0. P0 is 10 bar starting pressure, and temperature is 300 degrees Celsius. So we need to find the point, the critical pressure ratio P star by P0 for the flow rate to be maximum. So the flow rate will be maximum when this P star by P0 occurs at the throat point. P star by P0 is equal to 2 by 1.3 plus 1. Basically, the previous formula 2 by gamma plus 1 raised to 1.3 divided by 0.3. So this one will be equal to 0.546. Therefore, P star will be equal to 0.546 into 10. 5.46 bar. So the intermediate point, the throat point pressure will be 5.46 bars. If we try to plot that on an HS diagram, zero point 1 and the 0 and intermediate point star and the exit 1. So this pressure P2 will be P1 will be 2 bar and this P0 will be 10 bar, and we have found P star will be equal to 5.46 bar. So the nozzle, it's an isentropic one, right? So we have to determine at the point 0, P0 is equal to 10 bar and T0 is equal to 300 degrees Celsius. We get X0 will be equal to 3052.2 kilojoule per kilogram, and S0 will be equal to 7.1229 kilojoule per kilogram Kelvin. So at P0, P star will be equal to 5.46 bar. We calculate the SG, saturated gas, that will be less than the S value, S0. Therefore, S star will be equal to S0 equal to 7.1229, showing that this will be outside the vapor dome. Now we can calculate the our initial assumption that there will be some throat section. This will be a convergent divergent nozzle. Since the in between pressure P star is not at the exit, since it is at the intermediate point, we can say that this is a convergent divergent duct. Now we need to calculate the minimum area of the nozzle. For that, we have to go to the throat point at this star, S star and P star. We get H star is equal to the enthalpy based on stream table 2, and the specific volume is equal to 0.4125 meter cube per kg. Root of 2000 into H0 minus H star divided by 1/2. That will give the velocity V star at the throat point. So that will be equal to 540.91 meter per second. Therefore, given the steam generation rate will be equal to 1 kg per second. So that will be equal to A into V star divided by nu star. So therefore, A star will be equal to V star divided by nu star. We take it to the left hand side. So that will be equal to 7.626 into 10 power minus 4 meters squared. That is a minimum area of nozzle. So we found this by checking if it was a purely convergent nozzle, the minimum area would have been at the exit. If it is a convergent divergent nozzle, the minimum area would be at the intermediate. So we have to find the critical pressure using the formula and found out that this pressure is lying in between the input and inlet and exit pressure. So that means it's an intermediate point. So it's a convergent divergent duct. convergent divergent nozzle, and from there we calculate the in between points enthalpy, and using that we'll get the critical velocity at the in between point, and we get the steam generation rate. Look into the next problem. So look into the fifth problem. Steam expands in a set of nozzles from 10 bar and to 300 degrees Celsius to 1 bar. The convergent parts of the nozzles are sharp and frictionless. In the divergent parts, the friction loss may be taken as 0.15 of the isentropic enthalpy drop. If the steam flow rate is 1 kilogram per second and the initial velocity of the steam is negligible, find the minimum area of the nozzles. If the exit diameter of the nozzle is 25 mm, find the number of nozzles. So it's a convergent divergent duct. So we can denote 3 points as like this, and then HS diagram. So it starts from point 1, goes like this. And then 3. 300 degrees Celsius and 10 bar at the starting point. P star P is equal to 1 bar. So just like the previous case, we have to identify the in-between points. So P star, that's a throat point pressure, that will be equal to P2. We have found out that the ratio will be 2 by gamma plus 1, gamma raised to gamma minus 1 will be equal to 0.546. So we can straight away use that from the previous into P1 from the previous. So that will be equal to 5.46 bars because P1 is equal to 10 bar. H1 from the steam table 3052.2 kilojoule per kilogram. S1 will be equal to 7.126 kilojoule per kilogram Kelvin. That will be equal to S2 and S through S3 S. So third part, the second section is, first section is isentropic, and the second one there will be an isentropic enthalpy drop due to the friction loss in the divergent part. So from 2 to 3, there will be some friction associated with it. So then H2 is equal to 2916.2 kilojoule per kilogram. P star is equal to 44.72 into H1 minus H2 the whole power 1 by 2. That will be equal to 521.5 2 meter per second. Therefore, we can write V3 is equal to root of 2000 into H1 minus H2 plus 0.85 times H2 minus H3S. So the enthalpy difference in the second section. So that will be equal to 895, 894.79 meter per second. So we have got this velocity at the third point as well. We need to calculate the minimum area of the nozzle that happens at the point 2 and the number of nozzles for a given number of nozzles. So we can actually go from point 2 to point 3. So we actually need really need to know the third point's specific volume and the exact point, state point of the third point. So we need to identify where exactly it happens. So specific volume at the point 2 for a pressure of 5.46 bars and S2 is equal to 7.128 kilojoule per kilogram Kelvin. We know V star is equal to V2S is equal to from the steam table 0.416 meter cube per kilogram. So we know the flow rate, steam flow rate is equal to 1 kilogram per second. That will be equal to A star into velocity star divided by nu star. From here we'll get A star is equal to 1 into 0.416 divided by 521.52 will be equal to 7.98 centimeters squared. So that is the in between points throat area of the minimum area of the nozzle. This is the first part of the problem. Now we'll move to the second part. We know S1 is equal to S3S. So that is equal to 7.126 SF plus X SFG. So this will be equal to 1.3 plus X3S plus 6.05. Therefore, X3S is equal to 0.962. That is the dryness fraction at the point 3. Therefore, H3S could be written as the enthalpy at the state point 3 equal to using the saturated fluid enthalpies as well as the saturated and the enthalpy of vaporization. So that will be equal to 2587.67 kilojoule per kilogram. H2 minus H3 divided by H2 minus H3S equal to 0.85 plus H3 is equal to 2638.67 HF plus X3 into HFG. Therefore, x3 is equal to 0.984. We know the actual dryness fraction, so that will be slightly shifted to the right. Therefore, nu3 is equal to nu f plus x nu fg. That will be equal to 0.001043 plus 0.984 equal to 1.686 meter cube per kg. So using this one, we can actually determine the state point 3's area, that is exit of the nozzle's area. So 1 kg per second mass flow rate will be equal to area into V divided by nu. Therefore, A equal to, we know the specific volume, nu at 0.3, and V is equal to V3, we'll get A equal to 18.64. Centimeter squared. Therefore, this is the area at the exit of the nozzle. So this will be equal to n into pi by 4 into diameter squared. Diameter is given as 2.5. Therefore, in 2.5 centimeters, 25 mm. So therefore, we can write number of nozzles n is equal to 3.794, approximately equal to 4. So this is a straightforward problem that in which we have to find the minimum area of the nozzles. So that happens at the throat point. And then we have to calculate the number of nozzles at the exit. So for that, just like the previous cases, we have to find the state points and get the velocities, specific volumes of all the cases to find the area from the mass flow rate that is given, that is 1 kg per second. In this case, there is an additional thing of the isentropic efficiency of a 0.15 that also is taken into account here. So that's all for the first part of the problem. Now we look into the another question. I'll try to solve it within a minute. So the question is regarding dry saturated steam at 5 bar enters a convergent divergent nozzle at a velocity of 100 meter per second. The exit pressure is 1.5 bar and the throat and exit areas are 1280 millimeter squared and 1600 millimeter square respectively. Assuming isentropic flow up to the throat and taking the critical pressure ratio as 0.58, estimate the mass flow rate and the nozzle efficiency. So this is also a continuation of the previous questions. So 5 bar, and then there is this the throat point whose pressure is P star, and then the final stage with isenthalpic efficiency of this is with respect to the isenthalpic efficiency. Yes. So this point is 0 and this is star and this is 1s and 1. P star by P0, just like the previous case, its value will be equal to it's depend upon the gamma. So in the previous case, we had taken it as 0.546, but now this is a saturated stream. That's why gamma will be different. So that will be equal to 0.58. Therefore, P star is equal to 2.9 bar. It's a saturated stream, right? So correspondingly, we have seen that gamma value for the saturated stream is 1.13. So therefore, the 2 by gamma plus 1 raised to gamma minus 1 reduces to changes to 0.58. So S0 will be same as at S star at this particular point. That will be equal to 0.822. So this will be equal to 1.66 plus 5.344. That is SF plus SFG SFG times X star. So in order to find the dryness fraction of the point star, we will get X star is equal to 0.966, that quality of the steam at the throat point. Uh, Enthalpy using the steady flow energy equation between the point 0 and the star, we can actually determine the velocity of the state point 2, state point star. So that will be h0 into v0 square divided by 2 is equal to h star plus v star square divided by 2. This will give us v star is equal to, I'm not writing the intermediate point, it will be equal to 456 meter per second. So therefore, the specific volume nu star could be written as uh, ignoring the specific the saturated liquids specific volume, that will be equal to x star into nu fg. that will be equal to 0.966 times 0.6253 will be equal to 0.604 meter cube per kg. Then we can get the steam mass flow rate equal to A star V star divided by mu star. We know the area as 1280 millimeter squared at the throat. So it is 1280 10 power minus 6 into 0.456 divided by 0.6040. That's equal to 0.966 kilogram per second. So that will be the mass flow rate of the steam. So that is the first part. Now we have to actually determine the second part, the nozzle efficiency. Now we move into the the divergent part of the nozzle. So we know that S star will be equal to S1S will be equal to S0 equal to 6.822. From there we can get the dryness fraction of the steam at the exit of the nozzle. That will be equal to X1S into 5.789. So this is the SF SF and this is SFG. From there we can get the dryness fraction at the exit point of the isentropic process is 0.931. So H1S will be equal to HF plus X HFG. So using this 0.931, we'll get H1S as 2539 kilojoule per kilogram. Then we have to perform energy balance between star and 1 to get V1 square divided by 2 plus H1 is equal to V star by 2 plus H star. So in terms of kilojoule, we can write it as H1 is equal to the velocity for 50 squared V squared into 10 power minus 3 plus 2650. This will give us the value of velocity. So V1 squared by 2 into 10 power minus 3 plus H1 will be equal to equal to 2754 kilojoule per kilogram. So that is equation 1. So we'll get one equation by performing the energy balance between the point star and 1. And then another equation that we can get is, we know the mass flow rate of the steam 0.966 kilogram per second. That is equal to area at the exit 1600 into 10 power minus 6 into velocity divided by nu1. That implies v1 by nu1 equal to 603.8. So we have got two equations with velocity. This is with the nu1 and this is with the h1. So we have to use an iterative solver. To determine the value of the dryness fraction in this case, because we know the value of nu1 and we know the value of h1. So we have to use by using an iterative solver. We can determine the dryness fraction x3. So from the it depends upon u1 and h1, right? So from there we can get the dryness fraction. So ultimately both of the point depends only on the x3. X3 is equal to 0.932, and from there we can get nu1 is equal to x1. Nu1 is equal to 1.08 meter cube per kg, and h1 is equal to 2542 kilojoule per kilogram. Therefore, we can get the value of velocity. Velocity v1 is equal to 652.2 meter per second from equation 1. Substituting the value of h1 and v1 from this one, we'll get the value. Therefore, nozzle efficiency could be written as h star minus h star minus h1 divided by h star minus h1s. That will be equal to 2650 minus 2542 divided by 2650 minus 2539. So that will be coming around 0.973. That is a nozzle efficiency. So in this problem, we had to determine the mass flow rate and the nozzle efficiency of the second diverging section. So we had to determine the mass flow rate first. For that, we needed the specific volume at the point star. So for that, we have used a steady flow energy equation between the point 0 and star to get the velocity and dryness fraction The dryness fraction is something that we have obtained from the entropy balancing, and using that we have determined the mass flow rate of the steam. And the second one is a nozzle efficiency. So in the case of nozzle efficiency, so that is slightly complicated. We have to take into account the energy steady flow energy equation between a star and one, and then also we know the mass flow rate, and we'll get another equation between the velocity and the specific volume. So this is actually an implicit equation. We have to solve them iteratively to determine the state point at one. From there, we get the velocity and the enthalpy, and using that, we can calculate the nozzle efficiency. Look into this problem. This is a problem on steam turbine. Nozzle efficiency is given, nozzle angle is given. So maximum efficiency, we know what should be the nozzle angle. So try to solve it. I'll also try to solve. A steam turbine is to develop 8 megawatt of at 5000 rpm for driving a compressor. The steam enters at 40 bar, 500 degrees Celsius, and exhausts at 0.1 bar. The internal efficiency of the turbine is 0.85 and its mechanical efficiency is 0.96. We have to estimate the number of impulse stages required if similar impulse stages are used throughout. Assume nozzle efficiency as 0.9892 and nozzle angle as 15 degree, limiting blade velocity 300, and the blades operating at maximum efficiency. So it's mentioned the blades are operating at maximum efficiency, right? So for maximum efficiency, blade velocity by inlet velocity should be equal to cos alpha by 2. That is the nozzle angle. V1 is equal to VB divided by cos alpha by 2. That will be equal to 300 divided by cos 15 divided by 2. Therefore, the inlet velocity is 621.2 meter per second. That's so the blade velocity is given as for 300. Limiting blade velocity is given as 300. So we substitute that to get the value of the inlet velocity. Then we have to determine the enthalpy drop per stage. So that will be V1 square divided by 2000 into eta nozzle. Because so what we could write is that V1 square divided by 2000 equal to eta nozzle efficiency multiplied by enthalpy of drop per stage. So using that, you get this one. So these are equations that are derived for determining the enthalpy drop per stage. So this is enthalpy drop per stage. So that will be equal to 621.2 square divided by 2000 into 0.92. That will be equal to 209.7 kilojoule per kg. Therefore, H1 equal to, so enthalpy drop per stage is 209.7. So at the starting point, the velocity is 621.2. Turbine has hold 8 megawatt and develops 8 megawatt power. Enters at 40 bar and 500 degrees Celsius. So H1 for the inlet condition, so that will be equal to superheated steam 344.3 kilojoule per kilogram, S1 from steam table 7.09 kilojoule per kilogram Kelvin. S2S, that is the exit point isentropic the entropy at the exit point for an isentropic nozzle, that will be same as that of S1. That will be equal to 0.6493 x plus x2s into 7.509. So this is a SGSF plus SSG at the second operating condition, that is 0.1 bar. From there, we will get x2s is equal to 0.86. H2s will be equal to HF plus X HFG 86 at the second operating condition, that is 1.1 bar. That will be equal to 2246.5 kilojoule per kilogram. Therefore, H1 minus H2S will be the change in enthalpy during the stage. That will be equal to actual total change in enthalpy, not per stage. Total change in enthalpy. That will be equal to n times change in enthalpy H drop per stage. Therefore, from this one we'll get a this is 119.8 divided by 205.7 is equal to 5.72. So number of stages should be equal to 6. So it's a straightforward problem which for comparing two different cases, we know the enthalpy, we have to determine the enthalpy drop per stage and use the total enthalpy to determine the number of stages. Which of the following assumptions is to be considered while analyzing the flow through nozzle? It should be one-dimensional flow, isentropic flow, frictional effect is neglected, steady flow. All the four. Another question: which of the following statement is or are correct related to the effect of friction in the flow through the nozzle? With the increase in the friction of the nozzle, the enthalpy drop increases, velocity at the exit decreases, temperature at the exit increases, nozzle efficiency decreases. So we know that enthalpy drop that is required for developing work that decreases. That means that the amount of flow that will be converted to the amount of potential energy that will, the amount of pressure energy that will be converted to kinetic energy will decreases. So we ideally require higher velocity before it reaches the turbine. So enthalpy drop decreases, yes, because of the velocity at the exit decreases, yes. Temperature at yes, nozzle efficiency decreases, yes. Nozzle efficiency is actually given by this formula. The second stage minus first stage divided by second stage minus second stage minus last stage divided by second stage minus the isentropic of the last stage. So once the friction increases, the top the enthalpy change H star minus H1 star decreases. We maximum it can go is from H star minus H1s. For a compressible flow, the diverging section acts as a diffuser. If the flow is it's the opposite of the previous question, so it has to act as a diffuser if Mach should be less than 1. So in the previous case, we have seen a convergent act for this to act as a nozzle, the Mach number should be less than 1. So that completes the session for today. We have seen a few numerical type and multiple choice questions based on this week's lectures on nozzle efficiency, and one on steam turbine as well. We'll see next week with the tutorial pertaining to the problems of next week's lectures. Thank you.